All right, this is a pretty fun problem actually. What we have here is a square loop of charged wire here that's infinitely thin and has some length for each side that's equal to A. And then we're going to try to find the electric field at some point P, which is a distance Z above the center of the square loop. So that means that this side and this side are equal to each other, and they're both equal to A over 2 since they're in the center there. So I'm just put A over 2 right here. Right? And so, yeah, again, we're trying to find the electric field here. So since we have some symmetry going on, first thing that we're going to do is just try to isolate one of the sides and figure out what the contribution of that electric field is for one of the sides, and then we'll apply it to the full square loop, if you will say. So one of the first things I'm going to do is just draw a separation vector between some portion of the side and to the point that we're going to get, which represents one vector contribution to the electric field at that point. As you can see, it's in the center, and I'll explain, and that'll make more sense later on. But first, I'm just going to go ahead and draw our coordinate axis that we're working with. So this is going to be X, this is Y, and since we already have a Z component here, this is going to be in the Z hat direction. And so like I said, we're just going to first kind of just isolate one of the sides. I'll just do that side that I just circled. So here it is. I was a little too close to the last one. So since we're just isolating that, everything else still applies here. It is kind of shifted up and over to some point P here, which again is still Z, and this is still A squared over 2, and then I'll just go ahead and draw that separation vector. So curly R, fancy R vector here, right? And so now we're going to try to figure out the electric field contribution of one of these here. And we were kind of hinted at in the problem that we were supposed to kind of look at one of the results of the example problems. And the example problem, I'll go ahead and draw right now. The example problem had some sort of same sort of segment right here. Again, by the way, this is still A right here. So it had some length A, right? And this one was a little bit different from the one that we had, in the fact that we had it at, we were evaluating the electric field at some point P here. That was right over the electric, or the line charge that we have right here. Whereas in terms of ours is the same thing right here, except it's just shifted over A squared over 2, or sorry, A over 2, and then back up some direction Z. So in terms of this problem, actually, I'm sorry, this was actually in the problem, it was 2L in the example problem. And in the example problem, it was some value called Z, but since we're dealing with different portions here, I'll just call that Z prime right now. And so when you look at this, and they just remind you to try to use this and apply it to our problem right here, it's not, obviously it doesn't look the same because it's kind of shifted over, but it is the same if we kind of think about things in a different perspective, where if we just look at this, if we look at this portion right here a little bit differently, and we kind of change, we view it in a different world, where our world, instead of our coordinate axis being straight up and down, left and right like that, we view it in a world where the coordinate axis is, where the Z component is actually aligned with our separation vector from that section right here, right? So we look at it in this world, right? And so it's not going to be called Z hat, X hat, Y hat. We'll call it Z prime. Here we go. I should have just done this before. We'll call it Z prime hat, X prime hat, Y prime hat, right? And so in this world that we're looking at our problem with, we just go ahead and just rotate it here. Oops. We'll just go ahead and rotate it in this direction here, right? So now that we're looking at it, the line segment hasn't rotated, but this vector has rotated some distance, some amount of direction this way. So that is exactly what we did here. We're looking at this same problem right here, except this thing has been rotated, right? And in our world, our hat prime world, the point is now located above the line segment, but it still has a separation vector curly r, right? It hasn't changed. It's just rotate. It hasn't changed in distance. It's just rotated. So now it's just located straight up above here, right? So if we go ahead and look at this in terms of Pythagorean's theorem, if we want to find this distance, that distance is equal to, let's see here, is equal to, so the magnitude of fancy r vector is equal to the square root of z squared and a over 2 squared, so a squared over 4, right? And that's the same value. That's the same thing as this is valued at right here, because it's kind of, it's got this value, which is still z, and then this value, which is still a over 2, except we just kind of rotated it over, right? So I'll go ahead and leave that here. And we're just viewing it in just this world, except for this value right here. This coordinate axis is just kind of rotated to the left a little bit, or rotated along the coordinate axis here a little bit. So I'll just make it absolutely. So we just take this, rotate it over, so that this is now the same thing that we're looking at here. So we just did this and just kind of rotated it over. So now it's aligned up in this world. So this is like a separate perspective world than what's above over here, right here. So going back to the solution of this problem, in the example that we did in the textbook, the electric field was found to be equal to, in terms of everything that we wrote over here, 4 pi epsilon naught, of course, lambda times 2L, which is the distance of this line segment right here, z prime, which is the height of which the point is located above the line segment here, times the square root of z prime squared plus, we'll just call it like this, 2L over 2 squared, right? So this distance here, just divided by 2. That's what we found out. Oh yeah, it was in the z prime hat direction. So up in this direction, which just means it's pointing in this direction in this coordinate plane. Both the same thing, both the same magnitude, same direction. We just call it differently, just different perspectives. Now, the whole point is getting everything that we have in this world and transforming it to everything that was given in this world, right? So we're given z, a over 2, we're given lambda, and we're just going to try to, and we're also given z hat, y hat, and everything like that. So we're just going to transform everything in here, everything over here, into things that are in this world. So the first thing we didn't do, and we kind of already did that, is we have this right here. We can now transform z prime into terms of our magnitude of the fancy separation vector, which was found over here. So we know that what we did over here is that z prime, that distance, is equal to the square root of z squared plus a squared over 4, which is what we found right here. This is this distance, which is the same as this distance right here. Another thing that we did is that, of course, L over 2, that's the same distance of this line segment as a. So let's see here, L over 2 is actually equal to A in our world. So we'll go ahead and make those substitutions into this equation that we have right here. That 1 over 4 pi epsilon naught remain the same. 2L is now equal to A. Z prime is now equal to this stuff right here. So I'll go ahead and do that. So this is, let's see here, square root of Z squared over A squared over 4. And then now we still have all the rest of that stuff right here. Z prime squared is just equal to Z squared plus A squared over 4. And then finally, 2L is equal to A, right? So this is all equal to plus A squared over 4 again, right? And again, don't forget, this is important. This will be the next step here, is that this is all still in the z prime hat direction. We haven't done this transformation from this direction here to this direction here. Well, in reality, this direction here is actually this direction here, so it kind of look off in this world right here. So that's going to be our next step. The next step is just trying to define z prime hat in terms of everything that we have in this world over here. So we know that z prime hat is going to have, actually, this might be easier if I just take this now. Actually, oops, that's fine. I'll just move this over here. Let's move it right here. All right. Now I'll place, this is the prime world, and I'll go ahead and just properly align it right here. Move it over here. This prime world, whenever we think about the components, it's going to have some sort of component here and some sort of component here. Now this prime world has been properly transformed into the orientation of our original coordinate axis here. So the magnitude that this points over, and again, this is the same magnitude or direction and magnitude as our separation vector here. It's going to point here in the negative x hat direction in terms of our coordinate. So it's, then I'll go ahead and use white. So it's in the negative x hat direction, and it has some magnitude that's equal to a over 2, right? Some magnitude that's a over 2. And then, of course, it points in the positive z hat direction. That's some magnitude of z, right? So it's going to be z hat, right? So z prime hat is equal to all those directions that we have. So that's going to be z hat. So z hat minus a over 2 x hat divided by the magnitude of z prime, right? And the magnitude of z prime, of course, is we're just going to use Pythagorean's theorem. So this squared and this squared, so the unit vectors cancel out. So it's going to be the square root of z squared plus a squared over 2 squared. And we'll just go ahead and make that substitution into our value right here. So since all this remains the same, actually it doesn't. So I'm just going to go ahead and explicitly write that. One moment. So I'll go ahead and explicitly rewrite that. Coulomb's constant doesn't really change. We still have the lambda a times a very long denominator. I guess I should make that a little cleaner here. But so now we have the square root of z squared. This is, I'm just writing everything that we had before, except I'm going to combine these two into a squared over 2 now. And now I'm just going to finally make that substitution. Let me just move it down a little bit more, give some space. I'm just going to make this substitution in here. So what we have is our z. So we have a z component and a negative x hat component. Again, this is only just for this portion right here. I just want to make everybody remember. That's just for this portion, and I'll address why in a second. And then we have our square root of z squared plus a squared over 4 in parentheses, right? So, of course, this glob of constant, well, our glob of stuff is going to be multiplied by the x. We'll have a z hat and a x hat direction, right? But first of all, of course, this is going to be the same as this. So I'll just go ahead and write that down in the next section here. 1 over 4 pi epsilon naught lambda a. And so since this is the same as this one, that square root disappears, and all that's left is a quantity of z squared plus a squared over 4. This doesn't really change anything. We haven't gotten really anything new in terms of this stuff. So this is the square root of z squared over a squared over 2 over here. And now finally, each one of these is going to be multiplied by a z hat and a negative x hat direction. But as we can see here from up here, we have from symmetry, since we just calculated this from just this one line segment here, we know that this component is going to be pushing over here, but there's going to be an equal component that has the same z hat contribution, but they have opposing x hat ones. And we could also say that the one from this corner is going to have constructing z hat ones, but they're going to have different x and y hat directions, and that's going to happen all throughout this loop here. So the only thing that's going to be left is going to be all the z hat contributions. So at this point, we can just scoop up this z hat direction and just forget everything from the x hat direction from physics, basically, and just keep this z hat portion right here. This is only the z hat portion, or the only thing that's left over for the electric field at that point is the z hat portion, thanks to symmetry, of course. And then don't forget, finally, that we just calculated this for just one of these line segments. There's 4 of them. So if we take out 4, we have 4 different contributing electric field vectors or contribution fields from each one of these wire loops. So as you can tell, we're just going to multiply this glob of stuff by 4. I'll do it like this. We'll multiply it by 4, which of course is, math happens, and then this just ends up turning into 1 over pi over epsilon naught. And in the end of the day, this is our answer. So all it was just taking advantage of symmetry and then just changing our perspective of the things that we look at, and look at things a little bit differently, and just doing a little coordinate axis transformation. And then of course, using things that we already solved for previously in the example, and thanks to the hint, we were able to solve this problem with a little bit of imagination and ingenuity.